So a couple videos ago, we talked about strong acids versus weak acids versus negligible acids, and we're going to come back to that now, and we are going to talk about strong acids and strong bases. More specifically here, we are going to identify all of them, every single last one, because, as it turns out, there are only 7 strong acids, and I forget how many strong bases. So there's 7 of those as well, or is there only 6? Yeah, 6 strong bases. So there are a very limited number of these strong acids and bases. And again, just to remind you, the definition of a strong acid or base is any acid or base that, when you put it in water, completely dissociates. So every single last one of the molecules breaks apart into either H plus or OH minus, and then whatever the counter ion is. So when it comes to acids, the 7 strong acids are HCl, HBr, HI, HNO3, which is nitric acid, sulfuric acid, H2SO4, chloric acid, HClO3, and perchloric acid, HClO4. Those are the 7 strong acids. Now you will have to have these memorized, but there are only 7 of them, and they should be decently easy to remember, especially considering that these 3 are kind of grouped together on the periodic table. Because on the periodic table, beneath fluorine, don't count fluorine because HF is not a strong acid, but starting with chlorine, the next one down is bromine, and the next one down after that is iodine. So just hydrogen bonded with those 3 give you a strong acid. But then you do have to remember nitric acid, sulfuric acid, chloric acid, and perchloric acid. So if you have a solution of one of these strong acids, and let's say, for example, you know that you have 0.1 molar hydrobromic acid. Oops, that's a weird looking B. Sorry about that. There we go. HBr. Still kind of weird looking, but anyway. HBr. If you know you have 0.1 molar HBr, you also know that you have 0.1 molar H+. Because by definition, every last one of those HBr molecules that you put into the water breaks apart into H plus and Br minus. And so whatever concentration of HBr you have the same concentration of both of those ions. And so when it comes to finding the pH of a strong acid or a strong base, as we'll see, it's actually pretty straightforward if you know the concentration, because it's directly related to the concentration of the acid. So like I said, it's very similar for strong bases. The strong bases are actually easier to remember than the strong acids, because the strong bases are all the soluble hydroxides in the alkali metals and the heavier alkaline earth metals. So you do have to remember a little bit which of the alkaline earth metals count, specifically the calcium, strontium, and barium. But then the lithium, sodium, and potassium. And some people also include rubidium hydroxide in this as well. But since the book only lists the 6, we'll go ahead and just leave rubidium hydroxide off of there. Rubidium hydroxide is really rare anyway. Rubidium is not the most common thing to come across. So we're going to go ahead and stick with these 6. Technically, actually, francium hydroxide would also be a strong base, which means, you know, it would be very, very reactive, but if you came into contact with francium hydroxide, the reactiveness of the base would be your least worry, because francium is highly radioactive. So you'd be much more worried about the radiation poisoning than you would be about getting a little bit of base on your hands. So anyway, we're going to go ahead and stick with these 6 here. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide. Those are all in a one after the other on the periodic table in a column. Same thing with calcium, strontium, and barium. So if you can remember the starting point, it's just that one and then the next two molecules below it. Hydroxide are the strong bases. The thing that's a little bit different here with the strong bases versus the strong acids are these three. So you might have noticed they have two hydroxides. This is because each of them have a charge of +2. Each of the metals, I should say, have a charge of +2. So we have calcium, which is +2, strontium is +2, and barium is +2. And so to get a neutral molecule, you need two of those hydroxide molecules, or ions, I should say. Each of these hydroxides is going to be completely dissociated when the molecule goes into solution, just like the single hydroxide was up here. So the kind of tricky thing is, if we have, for example, 0.1 molar calcium hydroxide, what we would actually have in solution is 0.2 molar hydroxide, since we would be getting two of the hydroxides from each of those calcium hydroxides. So it would end up being double whatever the concentration was of the molecule, the whole molecule. Okay, so speaking of finding concentrations and pHs, let's go ahead and find the pH of these solutions here. So what if we have 0.040 molar HClO4 and 0.0011 molar calcium hydroxide? And I'm sorry that those aren't subscripts. Those should be subscripts. Why don't you pause the video and see if you can find the pH of each of these solutions. So go ahead and pause the video now. All right. So if we have 0.04 molar HClO4, perchloric acid is a strong acid, and so that means, by definition, we will also have 0.04 molar H+. And since the pH is just the negative log base 10 of that concentration, we can just plug that number into the negative log here, and we get, this has a pH of 1.3, well, actually, let's see, I only get 2 sig figs there. So it would actually be 1.40 is the pH. And that pH makes sense. That is a very acidic pH, and we're looking at a strong acid, so it makes sense that it would be 1.4. So in a similar fashion here, with the strong base, calcium hydroxide, we're told we have 0.0011 molar calcium hydroxide. This does not mean that we have 0.0011 hydroxide. We in fact have 0.0022 hydroxide. Since we get 2 hydroxides from each of the calcium hydroxides, we double the concentration to get the concentration of OH-. And at this point we have a couple different options for how to find the pH. We could take this concentration and plug it in to this. Yeah, ran out of space there. So that should be negative 14 here. So we're raising that to the negative 14. So we could plug that in here and solve for the concentration of H+, and then plug that into the pH calculation. Or we could find the pOH. So if we do that, so the pOH is going to be equal to the negative log of 0.0022. So we go ahead and do that real quick. 0.0022. That is going to be 2.66. And so now with the pOH, and knowing that the pH plus the pOH is equal to 14, we can find that the pH is equal to 11.34. And that pH, again, makes sense, because that is decently basic. It's not super basic, but that's a decently low concentration. And so it makes sense that it wouldn't be, way up at 13 or anything like that. That makes sense. That pH makes sense. All right. So hopefully you got the same answers as I did. What about this last one, though? What would be the pH of 0.03 molar HF? Well, if you just plugged that into the pH equation, you're forgetting something. HF is not a strong acid. Not every HF molecule is going to dissociate in water. Some of them will, and some of them won't. In fact, most of them won't. So, how do we deal with these weak acids? How are we going to find the pH of a solution that contains a weak acid? Well, you'll have to come back for the next video to find out. So I will see you there, and we will talk about weak acids.